now we can get into the really interesting stuff where we actually get to apply these forces to Newton's laws. Okay, so Newton's first law. An object at rest or with constant motion will remain at rest or continue with constant motion unless a net force is acting on it. So what does this mean in plain and simple English? It means that things continue to do what they do unless we do something to them, right? So if something's not moving, it's just going to stay there until something pushes it so it moves. Or if something is moving, right, it's going to keep moving until something does something to stop it or to make it move faster, whatever it is. Right, so in mathematical terms, Newton's first law basically just says F net equals 0, right, if something is at rest or if it's moving with constant motion, i.e. constant velocity, right? So for us, we're going to have the following strategy. We're going to find all of the forces in the x direction, or parallel to an inclined plane, and all the forces in the y direction, or perpendicular to an inclined plane, and we're just going to set them equal to each other. And that's again because the F net, the net force, the resultant force, has to be 0 if an object is not moving or it's moving with constant velocity. So when do we use this? Not moving or constant velocity. Then we know F net is 0. Let's see an example. So we've got an outrageously heavy light bulb, mass 2 kilogram, and it is hanging from the ceiling in that manner there. Right, so we've got to find the tension force in each of the wires that are going to be attached to the ceiling. Okay, now the point that we're interested in is this point here, because that's where the weight of the light bulb is going down and the tension of these forces are going up, right? So if I were to go, and I'm just going to draw that as the dot for my free body diagram, I've got the Fg going down here, and this I can calculate because I know it's an outrageously weighty 2 kilogram light bulb. So 2 times 9.8 is going to be 19.6 newtons. Fantastic, right? And then I know that I'm going to have an x component here for the 50, right? Well, for the tension. Let's call this T1. And let's call this T2. So this is going to be T1y. This is going to be, I called it Fx, but I actually now want to call it T2x or T1x. So let me get rid of that with my eraser. And then I'm going to call this T2x, T1x, maybe a T-rex. Okay. And then I'm going to do the following here. Okay. And then this is now going to be T2y, and this is going to be T2x. Okay, so I found the components that are horizontal and vertical, right? Or, well, not found them, but at least I know how I'm going to find them, right? Now, then I want to use what we've been using, but notice that that 50 degree and 20 degree angles are not actually in the triangles that I drew. Right, so an easy solution is to note that this surface and this surface, or these components, are all parallel to each other. So that 20 degrees and that 50 degrees, they're actually going to form alternate angles which are equal due to the parallel surfaces. So that's going to be 20 degrees and this is going to be 50 degrees. Okay, right, so now, because Newton's first law is in effect, right, I know that all of the forces have to be balanced. So the net force in the vertical direction must be 0, and the net force in this horizontal direction must be 0, because the light bulb's not moving, forces have to be balanced, Newton's first law. Right, so what does that mean? That means that the T2y going up, right, plus the T1y going up has to be equal in magnitude to the Fg going down. Okay, so that's my first equation where I've taken all the y components and I've set them equal to each other because F net has to be 0. And then equation 2 is going to be that T2x has to be equal to T1x, right? Because T2x is the only force going leftwards and T1x is the only force going rightwards. So for F net to be 0, they have to again be equal in magnitude, so they can cancel each other out. Now here we're trying to find T1, T2, etc. So it will be very useful if we had T1 and T2 in these equations rather than T2y and T1y. So I'm going to start here with the T2x. Now if I look at the T2x, I know that the 20-degree angle and the T2x are adjacent to each other. So for T2x I can use cos. So I'm going to say that T2 times cos 20 is going to be equal to the T2x. So I'm substituting that in where I see T2x. And then for this T1x, I see that that is adjacent to the 50-degree angle. So T1 is going to be equal to cos of, well, T1x is going to be equal to T1 cos 50. Fantastic. Okay, now I can do the same in the other equation. So T2y, that's now going to be opposite the 20-degree angle. So I'm going to get that the T2 times the sine of 20 plus, and now T1y, we're also going to use sine. So that's going to be T1 sine 20. It's going to be equal to FG going down, and I already found that to be 19.6. Okay, and what a wonderful situation we are in. This is because we now have two equations, and both of these equations have the same missing variable, T1, T2, T1, T2, right? And when we've got equations like that, we've got a particular tool that's available to us, and it's simultaneous equations. Okay, so we're going to use simultaneous equations in order to go and find the magnitudes of these tension forces. Right, so we're going to isolate this T2. So T2 is going to be equal to T1 cos 50 divided by the cos 20. Okay, so now in this other equation, wherever I see T2, I can go and sub in T1 cos 50 over cos 20. So I'm going to do that. So T1 cos 50 over cos 20 times the sine 20 plus T1 sine 20 is equal to 19,6. Okay, and now I'm in luck because now I have one equation that has T1 in it, and I can solve for T1. So to find the coefficient of T1 for that first term, we have to go and say cos of 50 divided by the cos of 20, and then take that fraction and multiply it by sine of 20. And so we get 0.22 or 2340. Okay, I'm going to 0.2340 T1 plus T1 sine 20. So sine 20, if I put it in decimal, is 0.3420. Okay, so plus 0.3420 T1 is equal to the 19.6. And now life is good because we can just go and say 0.2340 plus the 0.3420, because those are the coefficients of T1, and that's going to give us 0.576, right? So we get 0.576 T1 is equal to 19.6, and now we just have to divide the 19.6 by this 0.576, so 19.6 divided by 0.576. 576. Okay, and that's going to give us 34,03. Wonderful, right? And now to find the tension T2, we can just go sub this back in. So 34,03 times the cos 50 over the cos of 20 is going to give us, so that's the 34,03 times cos of 50 over the cos of 20, right, and that's going to give us 23,28 newtons. Okay, so it looks complicated, right, but at the very core of it, it's not that complicated because all we did is we applied Newton's first law. We said that if this object is not moving, the net force acting on it must be 0. which means that in the vertical and in the horizontal line of action, all of the forces must be balanced. So we said, fine, let's find all the forces and components of forces in the vertical direction and equate them to each other, those going up and those going down, because they have to be equal if they're going to add up to 0, right? And we did the same for the horizontal. Those going left and those going right had to be equal to each other, right? And then from there, it was just a bit of quick maths. Okay, so now it is your turn to put this to the test, right? Please pause the video and try this following exercise. Right, so well done on giving that a try. Let's see whether you were on the right track. So you've got the lamp is hung from the ceiling as shown in the diagram. The string rests against a wooden strut that protrudes horizontally from the wall. The tension in the diagonal part of the string is 50 newtons. Find the mass of the lampshade. Okay, so again, we've got this sort of thing going on here. And again, the point of interest is here because that's where it's hanging from and that's where the tension is and that's where the strut is pushing against the string as well. Okay, so Newton's first law, it's not moving. The forces are balanced. F net equals 0. Okay, so I know that this Fg going down has to then be the same as the Fy going up. Okay, and whatever force is being applied here by this strut going this way, I'm just going to call it Fs for force of strut, right? That's got to be equal to the Fx. Right? Now, we don't really care about the force that the strut is applying to that point there because we just want to find the mass of the lampshade, right? And to do that, we're going to use this up-down kind of forces, right? So we want to find Fy basically because Fy is going to be equal to Fg, right? So Fy is equal to Fg, right? And then to find Fy, all I'm going to do is I'm going to draw that there to make it clear that this is my force triangle there, right? And if this top angle here is 50 newtons, oh, that's not 50 newtons. Okay, now I've drawn a silly triangle. Let me draw it here so it's easier to see what's going on. Okay, I'm going to say this is the 50 newtons. I'm actually going to draw Fx here, and then I'm going to draw the Fy here, like that. Okay, that looks better. And then this is 25 degrees. Yeah, I prefer that. Okay, so then the 25 degrees is opposite Fy. We're going to use sine. So 50 times sine of 25 is equal to Fg. Okay, so again, 50 times sine 25 equals, and then we get 21,13 newtons. Okay, and then we know that Fg equals mg, right? So that means that this 21,13 has to be equal to the mass times the gravitational acceleration, 9.8. So if we take that 21.13 divided by 9.8, we get a mass of 2,16 kilograms. And that then is the mass of the lampshade. So well done if you got that.